because best to do during a discussion, I think.
Okay,
So
that's fine.
Go ahead.
That makes sense. So I just need to check where the.
So are you all well settled in your new place?
Well, no. Yes and no. So it's kind of complicated. So, but it's not a big deal. Okay, so here we go. Just sort of gray areas about how much to pay with rent. They seem to be very they're kind of fucking around, really, to be quite honest with you. So, you know, they state like, oh, we'll give it to you at this price. Then they so yeah, which I think is illegal, as far as I know. Anyway, we'll see. So a bit annoyed about that. So, but it doesn't really matter at this stage. We'll sort it out later. So there's really two things that I need to do. One would be to look at the I guess, you know, the kind of code behind this and the kind of outputs that we can get from the leptogenesis part. And the other thing would be to just go over the paper. Now, you see that, I mean, there is a bit of a problem with this because there's almost two versions of the paper now. Or, yeah, because I was working on it, and then I realized that there was an issue, so I changed some of the code, and then I was looking at the outputs, and I was like, that doesn't look very, that doesn't look like what I was wanting. So then I decided maybe I should revise part of the concept, and that meant to rewrite the paper a bit to remove things that weren't working. So so I kind of did start that, but now I'm sometimes you can be I don't know, you know yourself, you can be too hasty in editing stuff and like trying to find a solution to a problem that maybe didn't really exist. And so I think what I'll do for today's sort of presentation would be to just not focus on the revision part, because sometimes we can revise the wrong way, and just focus on the work. That doesn't mean to say that what I've produced here is 100% correct. I think there could be issues with it, and you know, most of those would probably be to do with things like energy conservation laws. You know, like, so you've right and left-handed particles, or and it seems like some of the rules slightly break some of the, maybe the conservation rules or some other issues. So yeah, these are things that need to be looked at, and I think we could do that today. So if we're thinking about what rules, so yeah, there's still a lot to this, which is pretty interesting. I don't know, I think we can go over it. I'll just share the screen then. I haven't, yeah, once again, I could have prepared this a bit more, but I should, to be fair, like, I do know all of this stuff, like I did write it, so I'm assuming it'll come back to me as we go.
Okay.
Okay, so there's the introduction. Like, obviously I don't want to go over all the text. It's just and we've been over most of the sort of particulars of this already in a previous live stream. There was a couple of additions that had to be made in my understanding at one point. So I was thinking about leptogenesis, obviously, as the creation of the leptons, sort of maybe around, you know, some point around the Big Bang, or afterwards. I think they have like the era of recombination or something. So I was thinking about it from the perspective of quantum mechanics and particle physics. But it's interesting if you actually look into the literature around this subject. It's a lot more to do with cosmology than it is quantum mechanics or quantum physics, which I think is kind of surprising. Oh, by the way, if you want to, this doesn't have to be like a presentation or anything, Rajan. This can be more conversational, like back and forth. So don't feel like you need to mute yourself or anything. And yeah, or okay, but I'll get on with it as well. So yeah, so then there's baryogenesis. I think that's the right word. It sounds like someone's surname, or someone's name. But so yeah, so like I say, it's a lot to do with cosmology, and then they have. So that's really not my focus so much, and I'm more focused on the particle physics side of things. And yeah, and the interesting thing is it does relate back to the 24 cell model particle physics that we talked about, which like expands into the 600 cell and 120 cell model, because it presupposes 8 new particles. I guess presupposes is the right word, yeah. And these, yeah, so because in the original 24 cell models, we had 8 particles, and we weren't really sure what to call them. They could have been, I think initially I was saying they were gravitons, but I think you wouldn't normally have 8 gravitons. Well, I suppose you could, maybe in super 8 gravity, there was a super gravity with where 8 was important. But yeah, and then there was dark matter. So these 8 particles would kind of be the they'd be partners to the gluons in a sense, because they're part of the same hypercube. They're sort of counterparts, if you like, to the gluons. So that is kind of interesting, and could help with baryogenesis then, because baryogenesis is obviously about the creation of baryons and neutrons and protons and neutrons. So if the gluons are very much a part of that structure, they hold the whole thing together through the strong force, and they mediate the color charge of the quarks. So if
I may interrupt. So you think that gluons came first or that quarks came first?
Okay, so there's something like this like obviously this paper is about leptogenesis.
Yeah.
So I haven't really delved too far into the baryogenesis part of it. Okay. So anything I'd say on that front would be kind of very speculative. But if we scroll down here, there might be something. So we have the left particle. So I think this one, no. Okay, here. So we have a quark, a down quark with a charge of -2, according to the kind of new charges that we've specified. And then we also have one of the new particles, one of the hexawen particles, that's also -2. So there's the idea that these two particles are somehow connected and they could decay into one another. So in that sense, there's possibly a decay mode channel from the hexawens to a particular quark. But I'm wondering if all 8 particles together might somehow all be able to decay or transform into gluons, and that if you had the gluons in the right configuration, they might generate the quarks by themselves, through interactions, and then that would cause the neutrons and protons. But like I say, that's not something that I've really, read up on to see if other people are working on that. There could be, very well thought out reasons for why that's not allowed. If that's the case, I haven't come across them. But then again, like I said, I haven't deeply read into it or researched it, so I don't really know. So yeah, so like I say, I'm just going to stick to the baryogenesis part today.
Okay.
But I think there was a couple of issues that progressed the work further, which made me think that it was worthwhile talking about this. Obviously, we have the sort of genesis of this model through the I Ching, and the fact that there was no order 5 differentials between any two consecutive hexagrams of the I Ching. So let's see. And then that, of course, led to the idea that there exists no number 5 hypercharge. However, and I'm not sure if I did. I don't think I did discuss this actually in the previous talk, because I don't think I was aware of it. But as far as I can tell, so for all matter particles of the first generation, we have a set of hypercharges. You can have a 0 hypercharge, which is technically just no hypercharge, so it's not really a hypercharge. So that's the way I'm coming at it. So you can have 1, 2, 3, 4, and 6, which if you take the absolute values of those, it's clear that there's no hypercharge of 5. And so, or that's the way it appears, but that's only for matter particles of the first generation. But if we were to include, let's say, antimatter particles. Now, I initially just assumed that we just switch the signs on these for the antimatter particles. But later on, rather than just make that assumption, I wanted to find out more about it. And absent of being able to actually calculate the hypercharges from scratch, which is something I should definitely look into, I just looked up some of the values for the antimatter ones, and it seems that they are all they're the same for matter and antimatter particles, which then changes the results of the hypercharges for the, or sorry, I should say that the weak isospins are the same, which changes the values for the hypercharges of the antimatter particles. And we get some pretty strange results. We get 0 again, that's not too important. We get 2, 4, 5, 6, 6, and 9. So as we can see, 5 is there. So this seems to pretty much would you say, like, discredit the whole premise of the approach if we can actually get a hypercharge of 5, assuming that this methodology is correct. So initially, that's what I was thinking, and I was going to retract my earlier work and say, okay, don't bother with this. This is a pointless road to go down, and just leave it at that. Then I thought, well, maybe we shouldn't go so far, because there's not a whole lot of antimatter in the universe that we're aware of, and there's certainly this asymmetry in the antimatter. So matter and antimatter, I mean. So it was thinking, I'd say it here, as it turns out, as leptogenesis is concerned with the asymmetry in the amount of leptons and antileptons created at the beginning of the universe, and the symmetry breaking of the King Wen sequence might simply be analogous indication of this process. So there's a kind of symmetry breaking in the King Wen sequence, and and this well, it's more about how the process that we're discussing with the lack of a hypercharge 5 or order differential of 5. So we're really saying that if the I Ching has any real correspondence to leptogenesis, it's only talking about matter, which kind of makes sense in the sense that, you know, matter is what generally makes up the universe. So yes, so that's my kind of logic with, so that we don't have to throw out the baby with the bathwater, or I guess we're not throwing out anything here. We're going to keep the bathwater as well. Just hang on to the whole thing. So, okay. Okay, there was something that I guess, right. So really, what I've done, I can stop sharing that. I suppose the main research probably does rely on the code at this point. See, I'm working on stuff and I forget what I've shared with you and what's just what's new research. So I'm pretty sure that we haven't looked at this. So this is the I Ching particle simulator. Have we looked at this yet, Rajan?
I don't remember seeing this.
Oh, okay, good. So let's get on with it then. Okay, so basically what we have is how this works is it works by a lot of lookup tables. So we have the interaction rules, and these are basically all the charges of the particles. Although I wouldn't take them on face value because they have to be unique in order for the computer to kind of differentiate between them. So, and then we have the particle conversion table, which basically just tells the program, you know, if you have a what's this called? A hexawen particle, a left-handed hexawen particle, and with a charge of 8, and one of, it's a bit hard to read this off the screen actually because they're not aligned. So
you do consider excuse me, you do consider hypercharge of 5 in this one, do you?
Yeah, you see, that's the weird thing about it, Rajan. I suppose, you know, what might be better would be to share my entire screen so that I can just flick them back and forth through documents faster. Okay. And yeah, that's going to make more sense. So yeah, the whole thing will be is basically predicated on this idea of no hypercharge of 5. So when we I'll just go back to that. If we postulate that there is a particle with a hypercharge of 5, then we have to kind of weirdly use this equation and work backwards. And when we work backwards, we're working backwards towards a particle that's either right-handed at the point that it's, that it's created, or left-handed, or matter or antimatter. And when we do that, for some reason, since we don't know the endpoint, so it leads us to sort of postulate that all of the particles existed. You see? Yeah. But to be fair, since we know that there is, according to one estimation, a particle with a hypercharge of 5, an antimatter particle, like I pointed out, we could just say we're done. We could just say, well, this is the particle with the hypercharge of 5, But assuming we're not going to do that, then we wind up with these 6 choices. And the idea is that when you have these 6 choices, it becomes like a more complicated matter because, okay, this one is anti to this one, but you also have anyway, it kind of gets complicated because there is no hypercharge for like certain right-handed particles, something like that. So you wind up with 2 sets of left-handed particles for the for like the matter and antimatter, and those two have to be also like antimatter for the other particles, which winds up creating as kind of more of a triune sort of, it's not just a duality of matter and antimatter, it becomes matter, antimatter, and something else, which we also see in color charge, I guess, is the best example. You've red, blue, and green, and then anti-red, anti-blue, anti-green. So it becomes this sort of triality, which then you can imagine would create, I think that therefore you get the interactions between those particles create the 8 gluons, even though you'd imagine it should be 9, but it's because 2 of them are linearly dependent on each other, with the central point. So, and that's kind of what we get here. We start off with 6, and then it becomes 8 because these interact to also form the triwen particles. So then we have this 2 or 6-2 split of these leptogenesis particles, and then we also see the same 6-2 split in the gluons, which is interesting. And then these 6-2 splits then are also reflected in the S8 matrices of the 24 cell. And the reason why the 6-2 split exists in the gluons is because if we think of the 8 gluons as vertices on a cube, and we rotate that cube so that it is, edge on, that symmetry, or no, is it corner facing? You're often talking about these crystal kind of symmetry groups, I think. So if we're just looking at the corner, one of the other corners is going to be kind of occluded. So you'll only have you'll only be able to see 7, which kind of works into the quaternions again. But oh yeah, no, sorry. Yeah, so that's one way of thinking about it, but it's simply the fact that because we have 8 of the gluons that come from 9 potential interactions. 2 of them are linearly independent, which means that 6 aren't, in a sense. I mean, they can all be combined in ways which are linear, but the other ones are just multiplications of each other in a sense. Whereas, so that's the 2 split of the gluons, just to clarify that. That's really what we're talking. Well, actually, there's another symmetry to do with the decay processes of the quarks, but we might get into that later. I think that was already spoken about in the previous one. So yeah, here we go. So we have an interaction between like an anti hexawen particle with charge 8 and a non-anti one, so just a normal one. And yeah, so then the computer can look this up and see that the results will be a photon in this case. So that is just an assumption that when the 2 of them are totally opposite, matter, antimatter, they will create a photon in the same way that an electron and a positron will do the same thing. But then there are other more complicated interactions which would have, an anti-hexawen particle interact with a matter hexawen particle of charge 2, and so we have -8 plus 2 means that we get -6, which would be an electron in this case. But otherwise, it could be -3, and then these 2 can interact, which is why they're extended out here to form electrons. Now, the group here is like a 4x4 group. This group in the center is more based on quaternions, and this group isn't really based on anything. I mean, we could apply, well, you know, we could apply like some group like the Klein 4 group, and I think that would work just as well. But I chose this kind of configuration because of like certain considerations that I have to do with these particles, that they have some sort of unique properties that allow them to do some fairly funky things, which may, like as I mentioned in the beginning, may violate some laws of causality, or not causality, but conservation laws. But I'm not really sure. I'm kind of thinking of them as like standing a little bit outside of that because of their sort of strange placement within the whole process. So, for example, with a triwen particle that's left-handed and another matter triwen particle that's left-handed, those two can interact to form an electron, but only a left-handed electron. Whereas the ones that are, you know, if you have a left and a right triwen particle, then you'll have a 50-50 chance of it coming out left or right. And if they are totally opposite, then they, similar to up here, they just eradicate to form a photon. We also have like anti-photons in here, but they're not really important. They're always just considered photons, really. Okay, so I think we can run this and see kind of output, assuming I haven't changed major variables in this, which could pose a problem. I'll just give you a look at the kind of outputs that this program gives. Okay, that sort of worked, although, yeah, we still have the same problem. So this is the number of particles that we started with. We see we just start with, let's say, you know, a certain amount, quite a small number, obviously, in the original case at the beginning of the universe. This figure could be like 19 billion or something rather than just 19. But and so we have different quantities of all of them. And then as we run the, now that is odd because there's more of these coming out at the end than there was going in. So that's interesting because I haven't noticed. So maybe I'm just going to run that again. So oh yeah. Well, see here we have the probabilities for what particles. So instead of having it just totally randomized, there should be, oh no, this one means that you get the same number of particles at the start, no matter what. And this one sort of randomizes it, but takes a random choice to get the probabilities. But so I think that's the one we are using, and so it'll be interesting to see why. Oh yeah, so this whole code actually includes the idea of chirality into the simulator, which is interesting, but a bit messier than I was thinking. So basically, if the particle is see here. This. So if the particle is moving through space time, it's going to oscillate either left or it's going to oscillate. Its handedness is going to change between left and right. That's all well and good, but if I have a table, some sort of table would be handy here. Okay, but when it's oscillating between left and right, we also find that it is the charges will also be different. So if we have the X particle, let's say the left-handed one, and it changes into its right version, then its charge will switch from 8 to 5 and back again. So that needs to be reflected then, because if there was no oscillation of the charge, then you could kind of almost ignore the chirality oscillations, you know, because if you had like 6 left-handed particles at the start and 4, or like let's say 6 right-handed particles at the end of the simulation, they would have all flipped, but they would have flipped in a kind of equal way, so it wouldn't really matter. But since the it also changes the charges, that therefore has a knock-on effect of what particles are going to be generated, whether triwens or photons or electrons or positrons. So it does need to be included, and my attempt to do that was kind of just using a load of rules like this group here, which is kind of messy and a little bit prone, could be prone to error. So that might be what we're seeing in the results here. So it's just or I may have also accidentally altered something. Well, let's see the results here. Oh, that's better. It's a lot better. But that doesn't mean that there isn't an error in there. Just because it works sometimes, but if there's times when it totally breaks, like we just saw, then that could indicate that there's something wrong with the code. On this occasion, this is fairly good results because we have generated some photons, and it generated basically, this is the kind of thing you'll see. It seems to like to create almost as if they're proportional to one another. So we have definitely less antimatter generated in this universe. There's more matter. Slightly more right-handed particles than left-handed particles, which is interesting from the point of view of like a chiral anomaly, but not really very many. And same here. But if we're talking about actual matter antimatter asymmetry, we would expect a much greater discrepancy here, correct? To the point where actually we wouldn't see any matter particles, antimatter particles at all, because it would be, I think it's like, is it 1 in a billion or something? It's massive anyway. So it might even be more than that. I'd have to look that up again though. So here we're talking about something that's not on that order scale, but since we're only generating like a very small number of particles to begin with, like only 99, then if we were to expect 1 in a billion particles to be created, we just wouldn't expect to see any antimatter generated at all. But so that sounds yeah, go ahead.
Yeah, one of the things could be that a small difference initially will steamroll to larger differences, as the process goes on. So there is a possibility by permutation combination, like it will start with a small difference, but the differences, as it goes on, the difference start increasing, which means that, you could have a small number of particles, the antimatter and the matter, little more matter than the antimatter, but that difference, it's like a chain reaction. That difference start increasing between matter and antimatter, and so that.
Yeah, I hear what you're saying, Raja, and that's a good point. So it reminds me of like chaos theory, or the butterfly flapping its wings or whatever.
Yeah.
And that could be the case, but excuse me, but you see, there's a bit of a problem there, because once you see, so we start with these particles, and what we want to happen is for them all to be eradicated because they cannot appear again. Yes? They don't appear in our universe. We just don't know what these particles are. So we should
could be
not be
part
able
of.
to. Sorry?
Is it possible? Yeah, is it possible part of the dark matter? They become dark matter in a sense. That difference.
Well, I don't know. It's just interesting that I initially thought that, you know, that they're positioned in the bosonic quadrant, or would you? Yeah, I suppose that's what you call it. That I was initially sort of blocking off for dark matter, and now we have these particles. So, I mean, maybe, but well, technically, all I know is that, especially later on, you'll see that there's a lot of strange properties to these particles. It's not just the fact that they are that they can oscillate their charge, or that there's like they're bosons, but they have chirality. That's another strange thing. There's also the fact that they're not dual particles, but kind of a tripart, more like gluons or the color charges in quarks. So they have a lot of kind of strange properties, but as we'll see, those properties get even weirder as time goes on. But so we begin with these. We want them all to eradicate, which in this instance they did, which is pretty awesome. But that hasn't been my experience running this program the majority of the time. So I don't know why that's the case. Maybe I fixed a bug without realizing it, or maybe I just got lucky in this instance. But one thing, yeah, go ahead.
Yeah, but gives them an idea that the dark matter may not be the origin. You know what I mean? So in the sense that it's quite, I'm thinking that this is a possibility. Just I'm thinking aloud.
Yeah.
That there could be matter and antimatter, but I would show slightly more matter than antimatter. That the differences, the antimatter sector of it become more and more dark matter, and that differentiation then created the barrier, the matter, and that differentiation between the real universe and the dark universe. So but you have to see how it, because how it steamrolls. You have to figure out the equation whether it can create that much dark matter is a big question. So
yeah, well, so here's another thing though, Rajan, to consider, that and this is a lot sort of, I remember when I gave this talk originally, or this presentation, Emmanuel was there, and he was very he was very good, like, because I was just throwing it all together, I think, the previous night, and he was very good in terms of like clear cut in helping out with some of the finer points, the more finessing the ideas, and some of the. Well, so the point he kind of raised was that once these particles are made, they're stable, So we wouldn't expect like the positive. I suppose we use anti. Oh no, these would be the positrons, wouldn't they? Even though they're anti. That's where it gets a bit confusing. Do we live in an antimatter dimension or not? Anyway, it doesn't.
Oh my god, yeah.
Yeah. So it gets confusing. So yeah, so there's the let's say these are the electrons, and they're not going to decay into these, and they're also not going to. Are they going to generate more of themselves? I mean, or if they're stable, then would we expect? I suppose they could be created more out of each other. But also going back to a point you made previously in I think it during the maybe last week, did you do one of the episodes on the history of physics? Yeah, and you mentioned about You mentioned quite a few things, actually. I rewatched that. It was very good. I was a bit more, I find myself more focused when I rewatch it. So, I know picked up on a few more things, which I thought were very good. But one of the things I do recall you saying at the time, anyway, was about the lattice kind of construction where you have a matrix. So we were talking about how you could have a particle simulation where the particles interact in one square, and then you just extrapolate then out over multiple, squares for like infinite distances. And so that's kind of what we're doing here in a sense. We have just oh, wait a second, what is yeah, so we have 10 by 10, so it's a universe of like 10 squares, 10 states. And so that's, and it's at what density? It's 99, I think. So there's going to be 99 particles in there to begin with that all eradicate. And then we just extrapolate further over the entire universe, and we would expect to have this fairly equal split. So that is that's kind of bad from the point of view of maybe the standard model of cosmology with as we talked about all the parts of the Big Bang that have some sort of charge parity and all of this. But from this perspective of the anamorphic universe model, it's not really that big a deal, because as stated in that, we have a universe that is a hypersphere that is capable of rotating inside out, essentially. And so according to that, sort of our Milky Way galaxy is basically centered on the south pole of the hypersphere. And pretty much it doesn't really move, I think, is the concept. So it's more like stuck to the tangent plane than it is the hypersphere. But when the hypersphere rotates, the concept is that everything that is above, like, so you know how you'll have your like 4 vector with 0, 1, 1, 1 or something, and those are going to be the XYZ coordinates. But we have nothing really in the W coordinate, so the 4th dimension. But we can, if we add a 1 to that, so we could have like 1, 0, 0, 0 being our XYZ W components. And though in that case, we're kind of up 1 dimension in a sense, although we're not really, because both are inhabiting the same basis vectors. So but basically everything that has a 1 at the start, let's say in the W vector position, is antimatter, and everything else doesn't. So when if at the beginning of the universe there was meant to be this rotation, although that may not have occurred, and then the idea was for symmetry there would be a second rotation back in. So all that matter would that's basically all the matter in the universe, like all the stars and galaxies, would then compress back into the center of the hypersphere, and the matter that's inside the hypersphere would go out, and then that would form a whole set of new galaxies. So the idea is that there's the exact same amount of matter inside the hypersphere as there is outside, and it's just an illusion created by the projection that it appears to be more. Okay, so to have a similar amount is actually not a problem. We would expect that there is a similar amount. Also, it's worth noting that any rotation of the hypersphere which brings the antimatter into the center will also, I'm conjecturing here, would also alter it from being antimatter into being matter. So we won't have an issue of like total matter antimatter annihilation. Now I don't know why that didn't run. Maybe it's because I didn't run it. There we go. So that's interesting, because what we see here is that everything eradicated just at the end. You see that? Like that is the last. Hang on, let's just check to make sure. Okay, those are the electrons and the positrons, and there's, yeah, so that's really, really lucky. Because I just ran it for 500 rounds. Normally, I would expect all of the leptons, or sorry, the hexawens and triwens to sort of cancel out. Well, I think it's around here that they all die out usually. But for some reason, they went all the way to the end, and we also got a perfect cancellation. This is like exactly what we would want and what we would expect from the start of the universe. We can also sort of go in here a bit and examine further what's going on. Looks like this is generating a load of photons at the beginning. So they're going to go up and then they go back down. Oh, they keep going. Yeah. So that's really it. So that took a lot of work, because initially, but I should probably save these actually, because this is an example of it working, you know, in a perfect kind of setting. And does that mean that it only works when we do you know, multiple how do you say, runs of it? So it's really a very chaotic procedure, and the universe we live in is like actually very random and chancy, and you know, you'd have to run it like, I don't know, 50 times in order to get the right results. Or, well, I suppose, yeah, so if I run it again, I'm guessing we're going to see a different outcome. Although I am a little bit perturbed about the fact that this ran on to such a right up to the end, which could mean that I need to increase the number of rounds just to be sure. So I'll do that. But we'll see. We'll run it again, and I'm anticipating that we're going to get entirely different results this time, and that it won't be a perfect cancellation, but you never know. Be good if it.
You are saving your code also, right?
Sorry, what?
You are saving your code also.
What do you mean selling?
Saving.
Oh, saving as I go. Yeah.
Yeah,
yeah, I do try and save. Did I didn't change anything there, did I? Okay, you see here. Oh yeah, that's okay though. That's just a parameter. I parameters like that I'll switch all the time. So here we see we did not get a full cancellation. Oh, and we still have.
Yeah.
So you can see here, because these are all antimatter, they're never going to cancel to create anything. And same with these. So they are just, the question is, so they will never interact with anything, and these guys will never. So this remnant here could be kind of dark matter in a sense, because
it's like epoch, I think, right?
Huh?
I believe that there could be different epochs. The initial epoch may be different, like I say, superluminar noisy thing, and then you have the probably hot PDP mechanism, things like that, that is creating this matter, you know, antimatter thing, and then you have the dark matter creation. So the epoch, then it pulls back, probably creates the dark matter, and then again, when the dark matter again, the whole thing comes out again. So it may be different processes that's going on. I mean, it goes back and forth. Initially it is that, but another epoch when it pulls back and become dark again. So the dark universe may not be, I don't know whether it's the first one, but it may be a consequence, especially with the gravity coming on. I think gravity is a secondary effect, So initially it may not be electromagnetic, and then the dark matter comes in because of the gravity, and then it pulls in, creates black holes and all those things, and then it creates, the whole thing. The black hole eventually, you know, becomes the what you call what we call it, the normally the galaxies that creates
Right.
supernova. Yeah, from black hole it creates the supernova, and then the supernova eventually creates all the galaxies, all those things. So I think so. It goes back and forth to different epochs that they have identified also in cosmology, right? I mean, they have 3 or 4 epochs. They say, where the
Yeah, that's
temperature,
right. Isn't there
yeah,
the recombination,
yeah, recombination,
right?
the temperature levels. Initially, it's
Fluctuate, they go
very
up.
hot. Then it cools down. Then becomes hot again, like that.
Yeah, you see, that's what I find when I'm hearing, and they're the kind of theories that they're trying to put forward. They have to be very careful that when there's this recombination that things don't get too hot.
Yeah,
And but I find there's something about that, like they needed to get hot again in order for this
yeah,
baryogenesis to happen, or whatever. But yeah, it's interesting because in this leptogenesis model, it's very simple how everything works, because
uh-huh.
there's really only, if you think about it, I can show you some examples of other um, simulations that I ran. So you can kind of see here. These are some other models. Um, well, I suppose. Okay, here's a good one because everything eradicated. Uh, so if you think about it, you might have like the first epoch would be this, although we're talking about something that's happening very, very quickly. And then the
Mm.
second epoch could be this one, and then this would be the third. But the point that's being made here is that in the first epoch, all of the hexawens eradicate to create the triwens, and then
Mm.
finally in the second epoch, the remaining hexawens and newly created triwens further eradicate to create the third one, which is just the matter particles that we know today. And
Mm.
so we have no more hexawens and triwens, and therefore we have leptogenesis. So that would, and here we see a much greater degree of difference. So just seem a little bit chaotic, though. I also tried to do a bit of a statistical analysis, which you can see there, although it's not hugely interesting because at this stage I hadn't incorporated the chirality into it. And if you were to do that, it would just get more complicated, but I'm not sure if it would really be very instructive at any level. But another thing that Emmanuel helped with was sort of helping to clarify well, the title of this is non-conservation of lepton number, which is an important part of leptogenesis. But Emmanuel is sort of good on making these Feynman, or they're not. I don't know if the correct name is Feynman diagram, but it's the one that we're stuck with. So let's continue. As apparently somebody else created them, but I don't know his name. So so we can see here we'd have like 4 of the hexawen particles sort of coming together to create a positron in this instance, or we could have 4 other ones creating 2 triwens, which go to create the the leptons. So these are the kind of tree level. I suppose you call these tree level diagrams or something. But
Mm.
they're I initially had them like coming together to form a stable particle and then breaking apart again, which isn't allowed unless you're talking about time reversal. But
Mm.
yeah, so for leptogenesis, it should only go one way, and all the particles should eradicate um, as we saw in the previous example, and as you see here, actually, this is another example where they all eradicated. So yeah, initially I was trying to use, well, I don't know if I covered this in the previous talk, but it was all about which symmetry group to use to create the proper interactions. And I found out that the best one was like, you know, the quaternion group. So basically this one, and that kind of forms the structure of this group. So the original particle simulator that I was going to work with was going to be all based on matrix multiplication. So I think in quantum mechanics, there's something about if you have, you know, if the matrices commute, then the particles interact, and if they don't commute, then the particles don't interact. But I found it was actually, when I was making the first version of the simulator, I found it much better to have the quaternion. I'm talking about quaternion matrices here, obviously. Or yeah, so I found it better that if they didn't commute, they interacted, and if they did, they didn't interact. And this is kind of obvious from these. So like this and this there's no interaction, but these ones there be so there's definitely no interaction along the trace of this matrix, which is also you know, where you'd expect to find commutivity. So it indicates that commutivity would not result in interaction as much. So, but I think where that's coming, that's probably more to do with like quantum field theory, where you have the gamma matrices, and you know, so it's getting into a much more sort of complicated area where this is not this. And anyway, I kind of, so ultimately I abandoned the use of matrices anyway, because I found that the Python computer programming language doesn't really handle strings and matrices and their conversions very well. So it all got a bit too complicated. So I settled instead for the kind of the tabular approach that I showed you, using I mean, lookup tables, and that worked quite well. So although there was a good bit of, I was thought it was going to be finished really quickly with it. I'm still in the process of writing this paper. That's why there's kind of placeholders here for the names of the graphs and stuff. Oh yeah, but then I did run it. This is still the version without any chirality in it. Like obviously we're just not switching the chirality at each time step as each time step is advanced. We just yeah. So in this initial one, but I took the average of 40 simulations and got this. So that was just you know, again, just to see what would happen if the universe started like multiple times. Would there be some sort of average results? But you can see it's pretty noisy. I don't know what to say about that really. And then this is the third version, which I assume contains chirality, but it might be something else. Oh, wait a second. No. What is the oh yeah, so the third version is just, yeah, we assigned, so this is just where you get kind of a random number of initial particles, but in the third version it was a constant amount. So you'd get like, you'd all like have 40 for each one or whatever. And the results were slightly different, but nothing really that important in terms of you know, nothing groundbreaking. So maybe an important sort of step forward, though, in the results here are the results of the hexawen and triwen particle masses. So the basic idea here was to just split the electron mass, because the triwen creates the electron. So we'd have a triwen with what is that? 255 eV, I guess, electron volts. And so from that, we can work out the mass, the energy, and the frequency of the particles. So a hexawen with charge 2 or hexawen 2 would have, according to this, a mass of 170 or 0.17 MeV, which is actually around the same as I think the muon. Yeah, it's basically the same. And then, yeah, so we get into the frequencies. One of the kind of interesting things about it is that the mass of the hexawen 8 particle gives this value, which is in MeV again. It's very similar to the energy in joules. When we convert the mass to joules, we get this sort of weird echo. But yeah,
So, the tau has more, right? Tau has more mass, or muon has more mass. I don't know.
The tau is heavier, so it could be the tau maybe that I'm thinking of. But I believe it's one of them anyway that has a mass value very, very similar to this, which is fine. So we see they do get progressively bigger, but also notice that there's negative mass values here, which isn't like it's not precluded by general relativity. In fact, we would expect particles with negative mass based on Einstein's equations for general relativity. And one of the big questions in cosmology actually is why don't we see any particles with negative mass? And in this,
will that be a dark part of the dark sector, the negative mass?
Well, yes and no. I mean, because like if this is correct, and let's say this group of particles has positive mass, this is negative mass, and they can all eradicate to form the triwens and then the leptons. If we're expecting them all to eradicate just at the beginning of the universe, like really quickly, and these contain negative masses, then that would explain why there are no negative masses observed today, because they're all destroyed. They were all used up in the creation of matter. So that is basically the concept. But this negative mass kind of needs to be, you know, it needs to be yeah, it's an integral part of this concept. But without a negative mass, this concept of leptogenesis and the hexawen particles will not work. And I'll show you why that is in a little bit. We also have these interactions where we have two hexawen particles with absolute mass and charge values cancel to form photons. So this interaction creates a photon, and this, then we can work out the frequency in hertz or terahertz of the photons that are going to be generated, and get, you know, 82 terahertz, 20, and 328. And then we can also eradicate the triwen with the anti-triwen, which I think is...
excuse me. Is it in the gamma or above gamma range?
Terahertz, yeah, I think it is. It's mentioned here somewhere that so we'd expect these four kind of bands of radiation at the beginning of the universe. So experimental confirmation of this I Ching leptogenesis could potentially lie in observations of the cosmic wave background. So we're looking for 4 distinct bandwidths at some time in the past. Should mention there that it is gamma radiation, but it doesn't. So I'm not sure why that's the case. But yeah, I believe it's gamma radiation. Now, I haven't read anything in the literature to suggest that there's these, these 4 bands or anything. In fact, yeah, I couldn't really find anything about it. Oh yeah, so there's the idea of negative masses would repel positive masses. This was disproven by the work of Leptogenesis. I think he's a German physicist. He proved that if negative masses were to exist, they would not repel ordinary mass, but rather remain stationary relative to the other particles' position. I wonder is particles plural there or not? But however, as a consequence of their interactions, they would move steadily and with increasing speed to the left. I think that's kind of funny, and that's a consequence of the differential equation. So, yeah, it's pretty funny.
Directly interpreting from the math.
Yeah, exactly. And the odd characteristic of positive and negative mass, this odd characteristic has not as yet been factored into the I Ching leptogenesis particle simulator, and to be honest with you, probably never will be, because I'm just not doing that. Anyway, it would require some sort of modular thing where they would just, I suppose there's modularity in it anyway, which is, that's the kind of lattice grid element where if a particle goes out the right side of the grid, it comes in the left side, and top and bottom and so forth. So yeah, I'm just not going to do that. There's an important point then about mass charge oscillation. So
is there a neutrino similar to neutrino oscillation?
Yeah, exactly. This is a good point, and one that Manuel also raised about the mass oscillation of the neutrinos, which seems like a very strange concept, but here we have it. If there's an oscillation, like a mass oscillation, yeah, you see, this might be the issue that I was coming to, and why I came to the idea of revising everything. Because if one of these particles changes chirality, means that it can change its charge. Well, that's okay, but we can see that all the particles have different masses as well, and some of them are negative masses. So that would mean that if it can oscillate its charge and its chirality in a sense, then it can also oscillate its mass, which is okay from the point of view of neutrinos. But yeah, so I don't think that's an issue either. That might not be a reason to maybe I'm right not to go for removing the idea of charge oscillation and all of this. I think that might have been a step too far. So I think we can leave that in. And so now not only do we have a set of particles with charge oscillation, but also mass oscillation, which, as you just pointed out, does link back to the neutrinos, and therefore kind of bridges, which means that the hexawen particles now not only kind of bridge between the quarks and the gluons, but they also share some very fundamental kind of relationship to the neutrinos. And that is interesting because neutrinos are very kind of fundamental or intrinsic in all of the research so far done by cosmologists and such into leptogenesis. There's an awful lot of talk about neutrinos and how they I've forgotten what their exact role is, but there is something there. Just can't remember what it is. If it's to do with ratios or something. Oh, here possibly. Oh yeah, I just mentioned that they play a pivotal role in a lot of the, or in some leptogenesis mechanisms. So I would have to find the references for that, maybe.
Does that affect that symmetry? The symmetry breaking
Oh, that's
involved?
probably, yeah, because there's no right-handed part, right-handed anti-neutrinos or something like that. It might be to do with that, yes. Here's just a quick example of the equating one of the hexawen particles with that it decays into a down quark and therefore splits off. So now we get the neutrinos involved, and the W bosons. But this can only really take place inside of a proton or a neutron. So there needs to be, in this case, 2 ups, I think, here. Yeah. So I don't think this alone would be sufficient to create baryogenesis, unless you had some weird sort of situation where a down quark met another anti-down quark at this point and created a meson, and then also one of the down quarks kind of decayed into an up quark, which met an anti-up quark and created a different meson or meson. And then those two combined with a third meson of a different sort to create, to all like split apart in different ways, like regroup to form 2 proper neutrons and protons. But again, that's just me looking for a way to come back to create leptogenesis, but there might be some reason why that's precluded. Possibly, the lifetime of mesons is a big issue. I think they can only last for about 10 seconds, which is perfectly fine. That's plenty of time in the early universe, I think, because those things would be bashing around into each other. Although, actually, come to think of it, in the very early universe, probably might be too much. No, they should be able to handle that, right? Because they're very stable elements. Okay, but I think it might be better if maybe the quarks are a bit like kind of ghost particles in a sense. They're sort of emergent out of the interactions between the gluons, and the gluons themselves are kind of take their form from the hexawen particles, and that might be the best solution. And I think, yeah, that probably is the best solution. Okay, so just going back then to the final thing, which is the mass charge oscillation. And this is pretty important. I guess I should just read through a bit of this. But yeah, okay, so in general, the particles of the standard model get some of their masses from the Higgs field. However, it is known that the neutrinos do not interact with the Higgs field. Therefore, it is still a matter of active research as to how the neutrinos gain their respective masses. It is this author's opinion that there must be some other field that the neutrinos are interacting with, opening up the possibility that a fifth force, a new set of particles, exists to bring this about. However, from the perspective of okay, so I'm going into the 600 cell grand unified field theory, which I mentioned earlier in the paper, and the 120 cell theory of everything. So there are no vertices left in those 2 models to accommodate any new particles or field. Therefore, whatever this field is, it must be generated out of the particles and forces that we already have. A clue to what this field might be comes from the neutrinos themselves, as they have the property of being able to change their mass through a process called neutrino oscillation. So this is what we've been talking about. Neutrino oscillation occurs as neutrinos travel through space-time. This is very similar to how fermions, right? Okay, so a lot of this stuff is kind of what we've spoken about. Okay, so here we go back to this kind of idea of a lattice, but instead of it being just like how do you say, how it's not just tallying up things like in a sort of statistical sense. This is suggesting that there is actually some sort of grid lattice that is foundational to the universe. So the intuition here is that there is some kind of grid or lattice substrate of space-time which imposes itself and perturbs the particles, causing them to flip rotations and oscillate their masses. This same substrate may also be responsible for the charge and mass oscillation of the hexawen particles. But what form does this substrate take, and how does it depend upon the other forces already present in the standard model? The answer to this question was alluded into the introduction section on the fivefold symmetries. So this is interesting. This goes back to your point about there being no such thing as like fivefold symmetries. I think you're talking about on a macro level, correct?
Yeah.
You're saying that on a micro level they do exist.
Different.
Yeah, I think you're probably right in that regard. It seems to me that since all crystals are formed from seed particles, which must themselves be quantum at some point, it should be possible to grow a macro-sized fivefold crystal. But perhaps I'm not right about that. And
yeah, when I was yeah,
I certainly haven't seen any very big fivefold crystals, I don't think.
Yeah. So when I was teaching the X-ray diffraction, I kind of mentioned people are not done that much, but at that time I remember mentioning to the students, because I was teaching in the university X-ray. I differentiated with the macro symmetry and micro symmetry, and people are not done that yet. And there's a famous X-ray professor. I think he liked it. He said, "I will be like your technician for your X-ray lab," because I made a very good point about the. I mean, I didn't pick up on that, but I think that would have been a great thing, because I think there's the micro symmetry very different from macro symmetry. Of course, later on, I'm doing the theoretical physics, but or the quantum mechanics, the other side. But once it's done, I think you can stitch back to the idea that microsymmetry may be connected with the quantum aspects, which now connects with the discontinuum physics that I'm doing with Emery. They may all add up. They may all add up, because I see I'm doing the case. Remember, I did the case 1, case 2, case 3, the sinusoidal. So in that, I find that one of them, the electric, is maybe we already I think there's a publication that shows that it's closely connected with the fine structure constant. So the discontinuum, the fine structure constant may be a manifestation, maybe a proof, maybe even evidential proof of the discontinuum aspect. Because the discontinuum, I'm finding when I do the graphs, that the discontinuum connected with the sinusoidal, the form of the sinusoidal, the phase and everything, it's closely connected with that, highly sensitive to that. So maybe a result of the discontinuum is what we see as a fine structure constant. So that's very interesting. That may be the microsymmetry aspects. What I'm saying. So in that one, you still have to do a lot of research. Maybe it's possible to have this fivefold symmetry.
So what are you saying, that the fine structure constant is somehow emerges out of the fivefold?
The discontinuum. The discontinuum.
Oh, okay. Yeah, interesting. I don't fully understand how that is, but
we are developing that. I think we may have, like, the coding we are doing, the graph we are doing.
Yeah.
From that, when they do a graph, I already see some correlation, fine structure, because it's highly sensitive. If I change a little bit, the whole thing blows out of thing. So it may be, when I do the correct numbers, it's so close to the related. I cannot say anything more, related to the fine structure constant. In what way, will come out later, but it's directly related to fine structure.
That's interesting. I mean, another thing that's interesting is that the 600 cell and the 120 cell that form the basis of these two different grand unified theories, and they're both five-fold symmetries,
Mm.
and as they're also, what I'm suggesting is they form like the basis or the bedrock of quantum
Yeah.
particles. So, but they also link then to you know, so they are the they because this is a theory of everything, it includes gravity. So we need the five-fold symmetry for gravity in a sense. Well, I'll get
Yeah.
into that in this. So the answer to this, wait a second. So, all right, what form does this substrate take, and how does it depend on the forces already present in the standard model? So that's the question. I guess, right, because we're saying that there's, yeah, because we can only use what we have, like including the gravitons. We can't add any more new particles except for the hexawen and triwen particles, which are now sort of eradicated, or would they be eradicated at this point? I don't know. Well, they're still in the mix at this point. So the answer to this question was alluded to in the, right, so we didn't, oh yeah, so now I'm talking about the five-fold symmetry crystals. The relationship between crystal symmetries and hypercharges was alluded to as neither are meant to contain order 5 symmetries. So they do, but they do occur in the form of quasi-crystals. So this also links to 600 cell. Yeah, go ahead, Rajan. Sorry.
Yeah. So I think the following way, from that. So the microsymmetry, let's say there is five-fold possible microsymmetry.
Yes.
But with the gravity and everything, the baryogenesis, it hides the five-fold symmetry, so that the five-fold symmetry is not, it's inside that, but it's not apparent to the real universe, or the baryo universe, so to say. So that may be in the
Okay,
macro.
yeah, that could be an interesting sort of avenue. I suppose from my point of view, this is this 600 cell and 120 cell thing. It's almost like a very abstract kind of thing. I'm not even really sure how it. I mean, it's more like just the symmetry group that contains all the other symmetry groups, and then connects the quantum fields to gravity, and then expands that out to special relativity, but not, and a bit to general relativity, I guess. But hasn't. What am I trying to say there? But it seems like, yeah, it connects it all, but it doesn't. Except in the case of maybe special relativity, and maybe it's not that concrete. Like it seems to be more of like an abstract, almost like a platonic form that exists but doesn't exist. Maybe it affects reality, maybe it doesn't. But it could potentially like I'm using it here. I'm using the quasi-crystal as the lattice substrate of space-time. And since the 600 cell is a quasi-crystal and can be used through cut and paste or cut and project methods, I think, to create quasi-crystals, it seems like this structure is the lattice structure of the universe, or this one. So in a sense, then, there is a direct correlation between this lattice substrate that I'm talking about and the so-called abstract platonic form.
It's an interesting thing.
Go
You
ahead.
pointed out earlier, I remember, about the hypersphere going inside out, right?
Yes.
So during that process, could be these things could be happening. It forms a quasi crystal, which indicates that it's going out. So then the five-fold symmetry gets hidden inside when it goes inside out. But the initial hypersphere may have the five microsymmetry with the five-fold symmetry. Then it goes inside out, become macrosymmetry. Then it hides the hides the five-fold symmetry, and that transition process may be where the quasi crystal may be occurring in the transition.
Oh, that's interesting, Rajan. I think you're right. I think there's something happens where there's like, but maybe it's not hiding it though. Maybe there's
hidden
like,
inside. You cannot see it. It's hidden
Maybe it's
inside.
not. Maybe it's not hidden though, because
No, or it could be transforming. Could be
yeah, just
transforming.
transforming out. Like, because let's say
Yeah,
if I take, I'm trying to think of like a good example here.
it's
Well,
like a phase
maybe I
transition.
don't really have one, but from the perspective of like, if I take the 120 cell, now that is a Euclidean 4-dimensional polytope. If I want to convert that, and that is the quantum substrate, I want to convert, which contains all the particles of the standard model, including 5 gravitons, which then later collapse down into just 2 for the spin 2 kind of part. But if I want to take that model and then introduce special relativity, I have to introduce a hyperbolic geometry, which requires, oddly enough, so this is almost like a hemi dodecahedron model. It's like, yeah, so a bit like how you would have a hemi cube. I think they call it hemi cube model. So, which is related to the quasi crystals as well. But once you expand, once you start bringing in hyperbolic geometry, you're going to get 4 of these dodecahedrons around a single axis. So let's say around the y-axis or the x-axis. And while that will not, I don't think that will hide the 5-dimensionalness of, or the 5-fold symmetry of the dodecahedron. Just thinking out loud here, but it does bring in like bring back the kind of 4-fold symmetry around a vertex. So, which is interesting. So it could be the case that somehow by expanding rather than hiding, but like just giving.
Yeah, transforming.
Yeah, exactly. You could also be right. It could be both. You know, you could be like hiding, expanding. Yeah. Oh, very good. That's something. It would be interesting if you were to, I guess, attempt to prove that or something. Use it because there's obviously a mathematical proof for why no 5-fold crystals can exist.
Rotation. Yeah. Rotation matrix.
Right. So that would be great if you could, I don't know, just like prove what you're saying there, like that as you get smaller, things get hidden. I think that, and do it mathematically, like using those equations. That'd be really cool. I'd give you a hand with that as well.
Yeah, we'll see. Yeah, as it progresses, when we start combining my time thing with your space thing, I think that would be probably the next stage, probably within the year.
Well, I think
then we'll start doing
I'm
this.
not entirely clear on everything that's going on with the time thing.
Although, it takes a year.
I support it, and I'll keep going, keep working on it. But I think this point you're making about the order 5, the 5-fold symmetry, and I think it would be a nice project to try and maybe prove that mathematically and also to demonstrate it on some level. So I think that's something we could definitely work on. I'd be really excited about that as a project. Okay, so just moving on then. However, it was acknowledged that the order. Okay, so we got to the quasi-crystal bit. Subject of quasi-crystals is an interesting one, and one that contains the concept of Fibonacci chains. So this is interesting, actually. There's a group called the Quantum Gravity Research Group, I think it is, or just Quantum Gravity Research, and they have a YouTube channel, and there's a number of people. There's a woman, I think they're right there in California. There's a woman called Fang Fang who she did, or I think I'm pronouncing that right. And basically they started looking into quasi crystals as a possible method of researching quantum gravity or something like that. And so you know, they have these structures of the quasi crystals, and then essentially, like, this is a visual depiction of a quasi crystal, And here, this yellow strip through this matrix or lattice, if you like, is what is known as a Fibonacci chain. So depending on, yeah, you see the way it's just going in one direction. If we were to flip that, you know, we could take this. This would be a different Fibonacci chain, and it kind of goes off like that. They're a bit difficult, tricky to comprehend, but basically they create chains like this, where it goes LL, S, LL, S, LL, S, and that just stands for long and short. So we can see here that this would be long, long, short, long, long, short, because this one's smaller than this one. And then it would go long, short, long, long, short. So this has so each of them have like a particular pattern.
Sequence.
Yeah. Yes, sequence, right. And you could also change it to like ones and zeros. And that's where Fan was working a lot with that. And I can't remember what her approach was exactly, but it is interesting. But oh yeah, you see, I mentioned it there.
Oh yeah.
Yeah, I haven't found the reference yet. There's also another guy who works in this field. So all right, I mentioned that I disagree with their approach. I couldn't tell you what it is now, but it didn't really. I kind of thought, like, you know, they're doing their best, pretty good, like better than no idea. But yeah, I just don't think it's right. So, but I do think that the Fibonacci chains. So if we look here, we have the we could relate this pattern to an oscillation of chirality. So instead of long, short, long, long, it could go left, right, left, left, right, left, left. You know what I mean? Right, like that. So as the particle is moving over the lattice, it goes right, left, right, right, left, right, right, left, right. You know, and that kind of thing.
The rotation, right? Is it rotation? Left and then right, like that?
Yes, yeah, exactly. It's the chirality. But if we apply that then to the hexawen particles, we also know that it's going to be changing its charge as well. So it won't be just left, right, left, left. It'll go 5, 2, 8, 5, 2, 8, and that will be the charge. Right, because let's say 2 is for the right-handed particle, but the left-handed particle can be either 8 or 5. So that's why it goes. So there's only left and right here, but there's actually 3 different types of charge here, because it can. There's two different left-handed particles with different charges, you know. So oh yeah, and then the masses would change in this way as it's moving along. So that's interesting. This implies that the structural nature of space-time can itself be likened to a quasi-crystal, which, if the reader is well versed in the just talking about the 120 cell model there, something which has already been right. Okay, so that's what I'm saying, that this perhaps it's not as abstract as it appears. It could actually be kind of fundamental. In fact, space-time is a four spatial dimensional hyperbolic dodecahedral tiling, which can be collapsed and gauged into itself, into its dual 600 cell counterpart. The collapsed part of the hyperbolic tiling contains the 5-dimensional structure of the gravitons, as well as their interactions with all the particles of the standard model, whereas the dual 600 cell component contains the spin-2 reduction of the 5D gravitons. However, the hyperbolic dodecahedral structure also contains the spin-2 component when the angle between the vertices is increased. Increasing the angle also has the effect of increasing time and decreasing space, just as in special relativity. Symmetry groups of both the 120 cell and 600 cell can be expressed in combination through the application of the S6 symmetry group of 720 elements. So by virtue of the fact that the 600 cell is a quasi-crystal, contains all of the fundamental forces combined, including gravity, suggests that the force which is responsible for giving mass to the neutrinos and the hexawens particles is none other than gravity. Alternatively, it could be surmised that the combination of all the forces, strong, weak, electromagnetic, and gravity, combine into the combination of those combine into the unified, cohesive framework of the 600 cell. Wait a second.
Is it possible to magnify this to some degree?
Oh, sorry. Is too small? Sorry.
Yeah.
Yeah, it was on it.
I was trying to say that before, but.
Oh, right. Sorry, I did not pick up on that. But
Sorry.
I'm in a bit of a weird headspace at the minute. So it could be surmised that the combination of all the forces. I suppose I want to say I've misworded this in this draft. So there's all four forces. So they all combine into see, I don't think this part is right. Combine into quintessential unified fifth force. So that makes sense, right? Because we have the four forces combine into a new fifth force, which could be the one that that is more than the sum of its parts, and it's the one that is responsible for giving mass to neutrinos. I'm not sure if that's correct though. But anyway, so this is the concept I'm working with. This theoretic fifth force could then be responsible through the application of the force shortening effects provided by the Fibonacci chain cell projections for the mass, charge, and chirality changes experienced by the hexawen and possibly even neutrino particles.
What will be the nature of the fifth force?
Right. So here I'm just thinking of it purely in terms of some sort of symmetry group. So in the case of the 120 cell, like I'm saying here, has these 5-dimensional gravitons, or well, 5 gravitons, and then they reduce to the spin 2 case in the 600 cell, but also in the special relativity version of this 120 cell. But you see that if we combine the 600 cell with the 120 cell, as they're both dual to each other, then we get 720, because 600 and 120 is 720 elements, which is the same as what's in the S6 symmetry group. So the total, this one contains the gut, this one contains the toe. So combined, we get S6. So we get the toe, you know, and then so the idea is that combined they create another symmetry group, which is another force essentially. And
I was thinking earlier, you know, like 20, 30 years ago, that there could be a fifth dimension, which is a sense, space-time. The fourth sense is a fifth. Could that be a sense force kind of?
No, I think you're definitely onto something, but you're like talking about like an advanced sort of subject.
Yeah.
But I think we're ready to once we've finished with this kind of thing, we can move forward into that. You know. But we need to say we have the answer. You know, it's done, and then people listen to us and go, oh, okay, they already solved that.
Some part of it,
Or some part. Like obviously, I don't have all of it, but like
part by part.
I will have I have like this the seed of something, and then the idea is to hand it over to the very knowledgeable physicists out there who do a lot of work with constants of nature and different aspects to like expand on this from this point. Well, maybe not the leptogenesis stuff, but certainly the you know, all of this 120 cells.
Quasi-crystal and all that.
Yeah, yeah, yeah. That's the more important part. That I'm not trying to promote the leptogenesis thing as like definite fact, but I think it probably could be. But anyway, I don't think it's like crucial or anything. And yeah, so but I think, you know, if that is then well, they're working on that and possibly, hopefully, generating something useful from there.
Oh, yeah.
I think there's a huge scope after that to like really open up physics more into the kind of thing you were talking about. For instance, let's talk about it now for a start. Or should I just finish this up, because I think I only have
Yeah,
one.
finish that up. Yeah, because I have few things, you know, very important
Okay.
things I found, but you know, we should not start until you finish it.
Right, no problem. So I just have one more point to make, really. So I think all I'm saying is that, and it's said here, so that these foreshortening effects provided by the Fibonacci cell projections. So it's like as the particle is moving here, it's like long, but then it gets squashed, and that increases its mass, let's say, and then decreases it, or it changes it. Moving this way alters its spin. Or it's, you know, squashing it distorts its charge, just like you'd imagine with a piezoelectric crystal. When we squeeze it, it generates more charge. And that this thing could be rotating as well, so it could like perturb the path of the particle in other ways that we're not expecting.
Distortion, create a lot of distortions.
Right. Yeah. So I think that is it. So maybe that change between as it's moving along these Fibonacci chains could be the force that I'm talking about. I don't know though, because I've now reached the edge of my. I suppose you're asking me difficult questions that I haven't really thought about. So that's it. I would just like to comment on what you said though about the sense thing, because if we think what is the most fundamental sense, I suppose one of them anyway is smell. I think they say that's one of the earliest. Is that right?
Yeah.
And how does the sense of smell work? It's basically these molecules sort of. So they have like, well, you have your olfactory senses in your nose, and the molecules fits into these kind of like a key into a lock. But it can only fit part of the molecule in, like whatever is extruding that'll attach to the sensor. So you could have two molecules that are very different, but with the same attachments, let's say. So the two molecules will fit into the sensor in the exact same way, but your nose is still able to say, oh well, this one smells like oranges and this one smells like lemons, you know, which are, I think, are two chiral molecules. And so the way it does that is by vibrating the molecule. So it basically just shakes it. But it probably sends those phonons that you're talking about through it, and then gets an echo back. That might be how it works. So that's interesting. That might be something you'd want to research more or add to your own list of research items. But I think of that. Let's say I have a crystal, yeah? So let's say the molecule is somehow crystalline, and we hit it with a hammer, it's going to like ring with a certain vibration, yeah? And then we have a different molecule with a different configuration. We hit that with a hammer, it's going to ring in a different note. So really, when we smell something, we think, oh, that smells like oranges, and this one smells like lemons or something. These are really just frequencies, even though we don't think of the smell as a frequency. That's exactly what they are, because the molecule is being hammered, you know. And so it is a frequency. And this is why, for instance, I've listened to classical music before, and you get this sense of synesthesia where I could listen to like some sort of contemporary composition of like classical music using violins, and I could hear the notes and say, "Oh, that sounds like oranges." You know, it sounds like
Mm.
lemons or limes. It has it's a citrus note. You know, and so this makes sense that there can be these crossovers of the senses, synesthesia, I think it's called, where we can transform or translate smell into a sound and vice versa, and that makes sense if smell is actually a frequency thing, because we all understand that sound is a frequency issue. So makes sense that, and of course, you know, sight is also frequency because it's dealing with the electromagnetic spectrum, and we can have synesthesia then between frequencies of light and sound, so and so forth, so on and so forth. But so what we're getting back to here is this kind of crystalline structure which might underlie underlie the senses. You know, that even then thoughts, like we could say, well, this number, I think this number has this color associated with it, or this word has this color associated with it, as well as the sound or something. And so then we get into the kind of concept of thought forms, and they could be, or memory, you know, how memory is stored in some sort of interlinking pattern of this moment connects to this moment, even though they might be years apart or whatever, and that kind of thing. So I think we could have a sense that your sense field is also, you know, combined in this. Maybe that is the nature of the fifth force. Is that what you think? Okay, cool. All right, so that's it. We're done.
Yeah.
That's great, Rajan. Thanks for that. It was
thank you. Good.
Yeah.
Interesting. Very interesting.
Thanks very much.
Very.
I was going to stop the screen there.
Yeah. So So if I continue, if I do the first one, it's a huge thing. I mean, it's just thinking aloud. It's unbelievable for me.
Wow.
Recently, I'm thinking about maybe energy is not conserved. Maybe time is that is conserved. You know, putting it in a very blunt manner. It's a very powerful idea. The reason is that if you think about a noisy superluminar general condensate, the energy is not conserved there. So which means that the energy that you see that the energy, actual energy, is quantum energy. You know, it is proved that it is quantized. The energy is quantized. So the quantized energy is conserved. The actual, the total, the actual continuum energy may not be conserved. Continuum energy part of the noise, and that's not conserved. So what it means is that really what is conserved is the time, because the quantum energy manifests into, see, this is a very deeper subject. I mean, just thinking about it. You know, I'm just putting it, it's the initial stages. It's a lot to be done, because it's a huge thing. So time conservation, I'm actually putting together a paper to suggest this thing. How I come from my tensor of time. The time is not scalar. You know that my few publications recently, that time is a tensor. Even I presented in our conference, the IC Fast conference, the time is a tensor. It's kind of proven. I have almost proven it. There are a few more things to be done, but which means that in that one I approved the time conservation, the law of time conservation in one of the papers.
I remember it. Yeah.
The time is conserved because of this the tensor nature. When you do the operation like Hamiltonian things like that, the action and all that, the time, you can prove that the time is conserved there. So the time.
Sorry, I just need to ask something. Like, how would you prove that time isn't conserved? I agree with you. I'd say, what does it mean? Like, if someone said time is not conserved, how would you show that? No, they're wrong. Like, how would they show that they're right? Like, is time? Do we ever say that time is not conserved? I'm just not.
Yeah,
I think what you're saying is interesting. I'm trying to apply it to something that
yeah.
I understand.
So we have to get into a deeper aspect. What is conservation?
Okay.
So that's how I'm looking into the philosophical aspect.
Mhm.
I like philosophy in some sense,
Well,
and that takes a
is
little bit
the
time, but I think it's important because what is what is time, then what is conservation? So more philosophical aspects, I had to go
yeah.
into more detail, what a brainstorming that,
Okay,
and then I can
you know,
connect because it will make
just
sense.
from a physical point of view, that or like a physics point of view, what are we talking about when we're talking about conservation laws? We're saying, oh, the amount of energy is conserved, even though it changes from kinetic
Yeah,
to potential, or the amount of energy, if the matter and energy conservation, or the energy of something that's rotating, so angular momentum
yeah,
conservation, so on and so forth. So yeah, so let's take that general concept of conservation laws as applied to physics, and you're saying, right, well, time is conserved. And I'm just wondering, so you could say, well, the energy of time, well, does that make sense as a statement?
yeah.
or
So
or like
yeah,
time flowing from the past to the future? You could say
yeah,
that the exact same amount of time that was contained in the past is contained in the future, or something. That could be a conservation law.
yeah, yeah,
Or
yeah.
is there more fundamental conservation laws that exist that you're drawing on that to do with time, or is this just totally new?
It's kind of new because of the tensor nature. And the reason I'm saying is a Planck
Yeah,
constant, right? The Planck constant says that energy times the time in the integral form is is constant, which means that if you take the differential equal to zero, it's conserved, right? So actually, it's the energy time that is conserved in that
right.
sense,
Yes.
right? But that energy is quantized. That quantum, what I'm saying is that quantum energy is the one that is going in there. So the quantum energy is a function of special type of time. You can E is a function of E of t, whereas t is a quantized time. So essentially, we can convert all E of t times the time into a time coordinate, right? So
Right.
everything becomes time. Everything becomes an integral of time is what h is, what Planck's constant is. So when I differentiate that, that becomes zero. So hence that time is conserved. Do you
Sure.
see that? That
Yes.
specific time is conserved. I am not saying it's the same as the continuum of energy is noise. The continuum of time may not be conserved, but realistically, the time when we talk about time is the real universe, is the baryo uh, universe, or it's not dark matter. It's not, the dark matter. The energy is not conserved there. Uh, the you know Even I don't know about antimatter, whether time is conserved, where the energy is conserved. But we know that in the real universe, it's conserved in the sense that, like you said, you can convert from rotational energy to translational energy, or mechanical energy into electrical energy, so on and so forth. But in that process, the whole thing is conserved. Although it is, that's what we use. That if I do a transduction, like if I use, for example, piezoelectric thing, so I put in the energy of vibration, right, piezo, and then I get the energy output in terms of the
Yes.
photons, the same way solar thing. I put that, I get in terms of the electrical energy, right? I put a photon energy, I get electrical energy, photoelectric effect. So all these time we use conservation of energy, that it's transferred from one to another, but that energy is conserved in that. But when you go into detail of that, it's a quantum energy that's conserved. It is not a continuum. The noise is gone as the heat energy. The reason I'm saying is a Carnot cycle. Why is it not 100%? You cannot have 100% because it converts to heat, which is leaking into the noise sector or the noise phase. So that energy is not conserved. But we are concerned about only the quantum energy. Yes, quantum energy is conserved. So we
Yeah.
have to look into that more detail. So that quantum energy I can express
Well,
in
wait a
10
second.
times.
Can I ask you a question there about?
Yeah, yeah, sure. Go ahead, please.
You're more of an expert on this than I am with the differential equations that you mentioned. So when you're differentiating that equation, it goes to zero. Is that like zero and a constant, or is that a constant, or
Because
is it just zero?
Planck constant. Because Planck constant.
No, but you know the way sometimes when you differentiate something, you know, you have this, and then there's C, and that C can be any value.
Yeah.
It does that come into this, or is that
No? I
something
mean,
else?
when I do the integral of the energy and time, it's just equal to Planck's constant.
And then, but then when you do the differential, it's just zero. There's no,
zero.
it's not zero plus a constant.
No.
Plus like C, you know, like just random.
No.
Okay, because I was just interested because that would change things, obviously, wouldn't it?
Yeah. I mean, actually, Wen Zong recently, it's an interesting paper he has put out about something about multiplying. Yeah, Wen Zong.
Yeah.
Multiplying the. You may have got that. Actually, he acknowledges. He acknowledged both of us in that one.
Oh, really?
Yeah.
Oh, great! No, I've been meaning to read it, but I've just
only two of us. I don't know why he didn't put Emmanuel or anybody else, but he acknowledged both of us.
Oh well, we should get him on anyway. I'm sure he's.
Yeah, I thanked him for that, and then he said that he was trying to publish in a very reputed journal. They rejected his thing, so he said we should push on. But he published in something else, you know.
No, he published in
the Canadian journle.
Canadian journal, yeah.
He's coming up in October. So I think it's important. We discussed that with him. I think he presented that where he said that Planck constant.
I think we introduced him to that journal, and
yeah. See,
so
I think that's why he's thanking us.
Probably why. Yeah, that's probably why. I'll have to read it by now, but that makes sense.
There got to be some reason, right?
Yeah.
Planck constant times the Hubble constant. He comes up with that. The whole thing is the real constant of the, it's probably quantum.
Oh, very interesting.
Yeah, quantum thing. So it's an important thing. Your derivation is very complete, very thorough. I like the math he does is very, very perfect.
Great. Yeah, I like you guys when you guys can talk on that level, of that kind of maths.
Yeah.
So I like hearing when you and Wen Zong chatting about that stuff. You were like, "Can you do that? And is that possible?"
Yeah, because
I'm kind of well, I'm not totally lost, but I don't even. Yeah, I don't have the familiarity with it.
I was kind of textbook type of thing, and I moved away from it. But when I was doing after my master's, after my undergraduate to graduate, I was so textbook. I will question everything that's not, like you differentiate that. I will even question, how you differentiate that. I'm very particular about the little details.
Yeah, that's great.
But it can get into, real headaches. But
fair enough. Yeah.
But I think it's right now when I go. I even said that questioned about the calculus itself. How can you do that? How can you do that? I was thinking at one point about that. Can you get around that instead of using the calculus, do the algebra? I believe more in algebra than the calculus because it's kind of I would think like a devilish or or kind of altered way of looking at things. It's not a real math. You are kind of, but the calculus does apply to specific things. I think one of the papers initially I did a PC model application. I have a detailed thing. At some point we'll go through that detailed way.
Yeah, I'd like to hear about that. But also, if you have some sort of critique on calculus or something, if you want.
Yeah, that one contains the critique on calculus. And I am saying how we should use it. That goes into detail about that, and I sent it to our. He's not directly interacting now, but you remember the person in Poland. We had some discussion of. He talks about electron. He had a lot of publication.
I don't know. I remember. Well, was it Alexei from?
No, not Alexei. The other person. It slips in my mind.
There was a guy. There was,
no.
There was
Pransky. Huh? Pransky. No.
Well, did we have him on this?
No. He didn't come on this one. Price Capsy or something like that.
Yeah.
Anatolij.
Oh yeah.
Anatolij.
You yourself and Emmanuel, I think, had some.
Yeah. We had interaction because initially he was one of the first persons I started interacting with, and he did kind of mentor me. He didn't discourage like other people. He was open to the things I'm talking about, and he did appreciate that.
People like you are, the people on sort of the fringes are ones will move things forward.
Yeah.
But it doesn't mean like we always have to agree or something, because
not at all. Yeah. They always, I believe in that.
Disagreements where like new ideas can come from, so that's good. But I think even more impressive is when after disagreeing for so long, when it starts to agree and then things start to come together, and then you go, oh, actually,
more beautiful,
and better off because of it, because of the amount of, it didn't just all happen, easily. It was like there's a lot of work, you have to work at something, and see through the sort of the I don't know, whatever it is, but eventually it's like the mist clears on subjects.
Yeah. It's like puzzle,
You begin to see other people's points of view, and there might be information that you're missing in order to correctly absorb what they're saying, and then over time you gradually get that information, or you realize, oh yeah, this person's talking about the exact same thing that I've been talking about for the last 10 years or 20 years. They're just so
remember
like this whole thing about just dismissing someone straight away. I mean, fair enough.
I don't.
If they're only like intersecting with your work on, like, here's one paper and they're asked to like just critique that, then if they say, oh no, I don't agree, I think that's okay. But depends, if you're dealing with something like if you were to write an entire book on philosophy, or something like that, which just sounds like you're getting more into that realm, and the chances that like everything in that book would be wrong.
I would actually, that's the one I like, the number one. I like to be a philosopher than anybody else. That's my life's goal. If I can be a philosopher and I can still live my life, I would think that's heaven for me.
Oh, that would be great.
Number one choice for me.
It would be great, though, Rajan, if you could write a philosophy book that was
eventually
completely wrong from start to finish, just as an exercise.
Yeah, history. The history of physics will help in that. And after that, we do the documentary movie, which I have advanced to some degree. Some initial things, scripts and all. I showed you something.
Your other idea was to publish volumes of 10,000 volumes or something like that.
Yeah. So in that,
back on some of our work that we've done over the years, and there nearly are, like, you can nearly start. I've got 100 papers or more, I think.
Yeah.
But around that, and I'd say you can nearly start like putting all the papers into a book and publishing them.
Yeah.
Anyway, that's another idea of yours. But
like a seed, it's like a seed. I think eventually it'll flower, it'll bloom.
Absolutely. Well, I think the seed has been built. Yeah.
Seed has been built, and excellent. So one of the things is that hopefully AI will help in that. What I am saying is that AI should develop to the level that you put your papers, 100 papers or whatever, it will churn out the correct way of It will do the editing and all those things. It will do the drafting, editing, and putting in the right format for the paper, for the book. And then the book will is nicely readable, understandable. It, it, it- you know,
I
it,
know what
it
you mean.
makes
Instead of
sense.
having to go back and
It
like
will take a long time for the
rewrite
AI to
everything
develop.
you've done. Yeah, that's a good idea. That's a very good idea. Okay,
Yeah.
Rajan. Now
Let
you
me let me show you the. I
yeah
think okay, the time, the particle thing. Remember, I
yeah.
talked to you about the particle thing. So let me show that before. I don't know
So
how
wait,
much time.
yeah, you have 2 points to make, do you? You have two discoveries that you've made.
Yeah. So one of them is the time aspect,
Yeah, which you just
which
mentioned.
needs.
But we
Yeah.
already, I think we already knew about that one, did we?
Yeah.
You would
No, no, no,
already
no, 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 no. The time conservation versus the energy conservation. Which will change the first law of thermodynamics. By the way, it will change the first law of thermodynamics itself. Um,
okay.
yeah.
Yeah.
So
I,
let me.
I didn't realize you were writing stuff out here. I'm gonna.
Yeah, that's okay. I'm just remembering something to finish that. Okay.
Okay. Well,
So this
are
is
you
okay.
using? I'm
I don't know
using
whether you
the
can see it. Can you
right.
see some of it?
Yes, I can kind of read that. Yeah. Particle
Let
property.
me put in the correct way. Uh, I don't know. It's a little better. Okay.
Yeah, it is.
Okay. So I'll call the particle property. I had to change that of physical constant, so to say. So I started plotting, and this is the initial plot of the the E or M we use normally, right, for particles, and versus the spin of the particle. So let me I think I had to pull it out to see the whole thing. Let me see whether that helps. Um, so this is the spin axis, right? So you have fermions like half spin, bosons are spin of 1, gravitons are spin of 2, right? So I am plotting E over M, which is initially the classical physics. That's the main thing. E over M of electrons, protons, all that is the most important thing, right? The charge over the mass. So when I plot that, I may have got it wrong here when we discuss. So it should be E, then move on. Tau has the higher mass. So it should be like this. I had to correct that. So when
Yeah.
I plot that, they all have the same charge, electrons,
Yeah.
muons, and the tau has the same charge,
Oh,
but
okay.
the mass is higher. So when I
Yes.
plot that, this curve will come down, right?
Well, why does the curve come down if the mass goes up?
Because the value of E
Oh,
or M
sorry.
comes down, right?
Right.
The
Sorry, what
charge
is
is
it?
the same.
Sorry, what is E? E in that is it charge or is it
Yeah, E is the charge. E is the charge.
so charge divided by the mass? The mass gets heavier, the thing
M
goes
is
down.
the
Yeah, that's
mass.
great. Okay,
Particle.
good.
It's
Yeah,
all
yeah.
the particle. Yeah.
Great.
So that's what I are talking. Very
Yeah.
fundamental thing. So when I plot these things can come down, right?
Yeah.
So
Sorry.
when I go to the bosons, what happens is E goes to 0, right? We
Yes.
think, and M go to 0, kind of, right? That's what we think now. We don't know. Photon does
Yeah.
not have a mass. So when I do 0/0, it's indeterminate, right?
Yes, correct.
I,
Yes.
so I present this indeterminate like this, like a
Sure.
shady, yeah, unnecessary. But when you go to gravitons, what happens is the E goes to 0, but M is not equal to 0. M is
Well, why
equal
do you
to,
say that?
because gravitons have mass.
Are you sure?
You are saying graviton does not have mass? I
Yeah.
would think graviton has mass.
Um.
They
Yeah.
are
No.
the mass givers. And
There's massive massive gravity theories for sure. So just because I'm saying that they don't doesn't mean that I'm right. There are people who are saying that there's massive gravitons, but in
yeah,
general, like if you're looking at string theory or something,
yeah,
they don't have mass, and that's like
graviton.
so if it's a spin 2 particle,
Uh-huh.
then it does not have mass or something. But you see this whole thing where I'm talking about 5 gravitons. I
Ah.
think when you have the 5 gravitons, they can have mass or something.
Ah.
There's something that goes on where the
Maybe
5.
it has your negative mass and positive mass may come there. They may cancel it there.
Yeah. See, I didn't really get into the whole point of why there was negative mass, but you can imagine it's to do with the interaction so that they cancel to create the right values.
Positive mass.
Well, let's just go with that we have massive gravity, okay?
Yeah.
So, that's okay with me. I'm not like ruling it out entirely. I'm just saying, yeah. Okay, go ahead.
I put a question mark there, so I have to check that.
Okay.
So is it true? Okay. So then what happens is E is 0, M is not greater than 0, right? Not equal to 0.
Yes.
Then it becomes 0. You see that?
Right, of course. Yeah.
So it goes up like that. So when you connect goes up like that, it comes down like that. It's an interesting thing. And from there, I come up with, I'm trying to figure out, it is connected with the discontinuum thing somehow. And then I say, remember alpha, I said the constant, and the discontinuum things, it is sine of some theta plus phi. This phi is the phase angle, right? Then the alpha is the fine structure constant. So alpha times phi is what I find from the plot. What I plot is very close to 1. Very, very interesting thing.
Sine alpha being the fine structure constant, and phi is what?
Phi is the phase angle.
Oh, sorry, Sorry, you read it there. Right, so then alpha times the phase angle is approximately equal 1.
1. So which means that the alpha fine structure constant is 1 over 5 or 5 power negative 1. So this is the discontinuum.
I thought the fine structure constant was 1 over 137.
Yeah. So this one is close to that, 138 or something. But
okay, so your phase angle is 138, 137.
So 1 over alpha is 137. Alpha is 1 over 137. So 1 over alpha will be 1 over 137, right?
Oh, right.
Yeah. So then you multiply that 130 is what you call alpha. Yeah. So alpha is 1 over 137 and phi is 138. Actually, because of the granular nature, because I have to split up into a stepwise thing, I get 138, but actual thing could be 137. But when I put 137, I get a lot of what you call divergence. So it's very, very precise. I had to put 138. If I change a little bit, everything kind of blows up. So I wondered why it is that accurate. So then I consider, that's close to the connector with the fine structure constant. That would make sense. So the fine structure constant is the splitting of that electric field. Kind of, this is a discontinuum of the electric field. Splitting of the electric field is what is manifesting as a fine structure constant. That made a lot of sense to me. So that is something.
That sounds really interesting.
Yeah, very, very
plausible as well. I like it. Well, I would comment on one thing though, that you're talking about the bosons being 0 mass.
Yeah.
What about the W plus and minus bosons and the Z?
Yeah,
boson?
that is. See, in this one, it could split up. You see that? This is like botched, right? You can call it botched or whatever. So the WC boson, it could clear some layer here. It could have a clear path where you have a clear signal here.
But wait a second. The question I'm asking is, so you'd have like charge. Well, what's the charge on the particle?
The photon is 0, right? Charge on the photon is 0.
Right. So you're talking about what's the charge? The charge of a
WC.
charge of a W boson. Well, if it's the plus boson, would have charge of 1, wouldn't it?
So then in that case, you will, let me put it here.
Let me just be sure about that.
I have to, okay, I will come to that. Why I'm writing like this,
yeah.
I'll come to that little later. But it's essentially your M. But why I have to write vector, we talked about a little bit. So spin conda here, let's say. Let's concentrate on the boson, spin of 1, right? So I have thing here. So if you have a W minus Z, WC boson, you say that it has a charge equal to 1, right?
No, I don't actually know if it has a. Well, are you talking about an electric charge? I don't think it does have an electric charge. I think it probably has a weak charge.
So let's say very close to 0, right?
All right, let's just say 0 because I really don't know yet.
Yeah, okay. And then M, you say may not be 0.
M is definitely not 0. It's around for the weak. The W boson is around 72 or something.
So then it is going like this. It is 0 here. This is WC boson.
Right. Yeah. So that's what I'm saying. So there is a 0 there. That doesn't. So it doesn't necessarily have to be the graviton that creates the 0. It could be
could be WC boson.
W or Z. Yeah.
But here also it could have another 0 here. So it could go up here and create another 0 here. So they could be 2 zeros.
Oh, okay. So yeah. Just thought I'd point that out. That's fine. Yeah.
So actually we can do a spectroscopy, use this thing to figure out these things. Some kind of a spectroscopy you can develop to figure out, much like the LHC do this to figure out these things that I am saying. So we can actually get a very good idea of.
Well, no, you see, there's a problem here because why are you running the? What's your x-axis? Is that energy?
Spin, the spin quanta number, spin number. Just a spin, like.
Oh, I see. Right, but how are you going to? How would you? Well, like, let's say if that was energy, okay, Rajan?
Yeah.
At the bottom, then all I'd need to do to plot your graph then would be to turn the dial up on the particle accelerator, and then we could just plot it on the graph. But if it's spin, how are we measuring? Like, there's no dial that I can turn.
Yeah, that's what we have to figure out. How to measure the spin. It's a magnetic.
Measure spin, but we measure it on a single particle in space and say, right, that particle has spin 1/2, or this particle.
Magnetic moment, right? Isn't it magnetic moment?
Something like that, yeah.
Yeah, it's a. I think it's very closely related to the what you call the Bohr, closely related to the Bohr magneton, I think.
Yeah, I don't know. It gets kind of weird. I mean, you got the spin 2 particle there of the graviton. That's obviously never been measured because they've never found
that's
the
the reason.
graviton. But the whole reason why they come up with the spin 2 is because of is something to do with relativity and the tensors rank order 2 or something like that. So so it seems to me that spin and it doesn't always have to be measured. I don't know. So it's
symmetry, right? Yeah. Because you have pi-fold symmetry. You rotate to get the same structure.
Bosons with spins. Aren't there a lot of bosons with spin 0? Or no? A Higgs. Higgs is spin 0, isn't it?
What is spin 0? What is the particle with spin? Huh?
The Higgs. The Higgs boson is spin 0.
Yeah, Higgs. Yeah, Higgs.
So if the Higgs is spin 0 and it has a mass of 126 GeV.
So here it could be like this. So I'm saying like this goes up, right? With the electron has here,
Yeah.
the muon has here, tau has here. So the Higgs may be up here somewhere.
Well, wouldn't the Higgs go to zero as well?
Well, does it have zero charge, zero mass? Higgs.
No, it has positive mass, but as far as I know, it doesn't have a charge.
So then it will go like this. It will go like this. You see that? So you get many zeros. It
Yeah.
goes up, come down. Goes up, come down. Goes up, come down. Could be that way.
Okay.
So that would make sense because it's oscillation, right? And it could be the I don't know. I'm just guessing. Neutrino oscillation may be connected with that. But let me come to why I'm using the vector. Remember about vector? I said tensor degradation, right? Then I came to, oh, it should be a vector. It could be a scalar. And you suddenly said that's what you are talking about many months.
Oh yes, yeah, I remember that.
Okay.
Yeah.
What is the difference? So I put a question last time. Is mass a vector? Right? The answer is the following. Okay. Suppose I am measuring and I'm reporting as a scalar mass, let's say 100 grams or 100 grams, which is 0.01 kilogram. Let's say that is the electron mass, that's some mass. So electron has what, 10 to the power minus 31 or something kilograms for the electron, something, electron mass of an electron approximately. So this is scalar because of the following. It becomes actually a vector with reference to a reference frame. So electron, so we have to define a reference frame. Okay, let me put a reference frame, rest mass, things like that. And I am measuring with reference to a reference frame, I am measuring a mass. This mass is actually a vector. When I am measuring with respect to a reference frame, that is a mass vector. This is a mass vector.
Okay.
And that's why weight, for example, we are measuring weight, for example, is a vector because we are measuring matter with reference to gravity. Okay, so whenever we have a reference frame, that automatically becomes a vector quantity, and then we have to find the absolute values to get the scalar mass. So that's why I feel when you take out the absolute values, you can have negative or positive. You can have negative or positive mass. But for each one is different. For example, for electron, I think it's with reference to photon. This could be a photon here. So we measure with respect to photon, and this electron here. So the reference frame keep changing depending on what we are measuring. For mass, it is gravity. The reference is gravity for mass. For electron or for electromagnetic, it is with reference to photon we are measuring. So that E minus then is with reference to a photon. And that's a very interesting, when I think about it, it makes a lot of sense. So the reason is that the reason why the vector becomes like the electron is, I can just write it 10 power minus 31 kg minus 0. Okay. But the 0 is important when you talk about the vector. When I write it as E, which is a scalar mass, I just write it as 31. So in value is the same, but this 0 indicates that I am measuring with respect to a reference, which is like a photon. That's a very deep concept. I think that might help understand, because this is a kind of math you need to understand why there's negative mass, positive mass, why the electron, the mass of the electron, and why there is a direction of time. Why the time has, for example, you think of that as clockwise or moving forward, right? We don't say there's a negative time. The time doesn't go backwards. And that may be the reason also for the matter-antimatter symmetry. So the antimatter symmetry then keeps such a way that that measures the time, which is now I'm saying the time is a vector. So the time, let me pull out another paper. So time is a vector.
Yeah, but isn't there the whole CPT thing?
Yeah, the CPT, I convert. Yeah, that's an interesting thing. Another thing. So the time, remember, uh, time is a vector. It's a degraded tensor, degraded time tensor.
Right. Yeah.
Okay. So time tensor is like this, like approximately the 6D virtual 6 dimension.
Yeah, I'm not sure about time being 6 dimensional. Is
Six
it not?
rank. No, rank.
Don't we generally just think of it as 2D?
No, rank 6.
Do
So
you think of
rank
it as,
6.
don't we normally think of it time as like 1 dimensional in a sense, or 2 dimensional, because it only has forwards and backwards?
Yeah. But actually it should be rank 6.
Yeah, but
But we need to.
where are you getting that from? I don't get it.
I have in my publications. I already put the publication.
But okay, but how do you prove it? Like,
Yeah,
how do
in
you
that
do it?
paper I have shown how it becomes like that.
I
I have
know, but
shown.
I don't follow. Like what? Like I'm not sure I follow.
No, rank 6 tensor, because you have to consider your Euler angles. The time also is connected with not just a Euclidean. So Euler dynamic coordinate. You need dynamic
What are
coordinate.
Euler angles?
So you have the XYZ, right? XYZ,
Yeah.
and then that itself has 3 dimension, right? Then I say why you need the additional 3. I have to bring out that paper to show
Okay.
that.
Maybe another time. But
Yeah, another time. But essentially what we are dealing with for our thing is time as a vector. So a vector which is only like forward and backward. So time will go forward
yeah.
and backward. Okay.
Okay, but in general, we only see forward, right?
Yeah. So the time vector. So that's the whole thing. So this is what time vector is. Okay. Time vector says it can go forward and backward. Okay. But why we see only forward?
Yeah. That's the big
Okay.
question,
Why we
right?
see only forward
Yeah.
is where the real universe and things like that. Okay. So that has to do with reference frame. So what is a reference frame for time? It's a gravity, right? I told you
Okay.
gravity. So I have gravity here.
Yeah.
Okay. It's a reference. Gravity cotton cord. What exactly you have to define? Then I have time here. Okay. So this is the forward time. This is the time that is going forward for gravity. Time of gravity. Okay. And can you see that? Okay. So the
Yes.
gravity says we have Earth gravity, right? The Earth here. Gravity can work only one way. It only centrosymmetric. I don't know what you call it.
Oh, yeah. I know what you mean.
So it works only one way. Because it works only one way, the time also can work only one way.
Oh,
You see
cool.
that?
Yeah.
Suppose I have anti-gravity, I probably could go negative time, but anti-gravity does not exist. The
Okay,
gravity
well,
that
that's
exists.
interesting. Yeah.
Yeah.
It's a
So the
good point of view
gravity
that
is
you
the
find there.
gravity defines the direction of time.
Okay. Yeah. I'm down with that. That sounds reasonable. This sounds like a good.
So that is the reason time goes only in that, because of the gravity, which
Okay.
is where the real is the time goes only one way. The gravity does not allow the time go backwards.
Okay.
So that's the sense.
That's
There are a
good.
few
Yeah.
things, but I don't. I think.
I like that. There's a logic to that.
Yeah.
One thing I will say, Rajan, is that I just looked it up for you, and the W boson does have a charge. It has a charge of 1 or -1, and it has a mass of around 80 GeV. So you're going to come out at 1 divided by 80.
So E equal to -1 WC
or -1 divided by 80.
How much is that? 80?
Yeah, the mass will be around 80 GeV.
80 GeV. Okay.
Yeah, and then so for the Z boson, it'll be 0, so that'll just go to 0. But the other one will be
W. Okay, W. Okay.
Yeah,
so,
W plus and minus. So the W plus boson has a charge of 1 and a mass of 80. W
let me write it here. So
yeah.
Let's start over here. I don't want to clutter that place. Okay, let me start a new one.
Okay.
I like this one. Should use this. The spin conda number.
But actually, yeah, a spin. It has a spin of 1.
Oh, really?
Yeah.
Yeah. Spin of 1. Yeah, I would think so. Yeah. So E of W plus is +1, right? And then M of W plus is, how much is that?
Oh, 80. Yeah, just around 80
GeV.
Yeah.
And then E of W minus is -1.
Right.
Then M of W minus it's again 80, right?
Yes.
Okay, 80 GeV. Then E of Z, C boson plus, is it plus?
It's 0.
Is 0. E of Z is 0. And then M of Z?
91 GeV.
Oh, it's very high. Okay. Now when we plot this one, E over M, what happens is that for this one is 1 over 80. So I need negative axis. I need a positive and negative axis.
Yeah, that's right, because it's going to go below the positive axis, isn't it?
I had to put the actual numbers. So
what's on the what is the y-axis then?
Y-axis is E over M. E over M.
Oh, okay. Charge divided by mass.
The spin. How do you write a spin? What is the symbol for spin? Is there a spin? S? Is it just S or?
I think it's just S.
SQ or QS, something like that.
I can't remember actually, but I think it's just S.
SQ. I will just write spin conda. Okay. Spin SQ number. Okay. So when I plot for EW plus 1 over 80, somewhere here, let's say, -1 is somewhere here. So this is my W plus, W minus. Then for EZ, it is 0. Okay. And M over Z. Okay.
That's correct.
Oh, how about a spin? What is the spin of? Is there a spin for W plus, W minus, and Z?
Yeah, they're all 1, aren't they?
They're all 1. Okay.
Okay, Rajan, I have to go now.
Okay. So now it becomes like this. It becomes something like this. The W plus is here, Z is here, W minus is here.
Oh, okay. Well, keep working on that and let me know how it goes. Good talk.
Excellent.
I think you covered everything, did you, that you wanted to talk about?
Yeah, essentially. So next week I'll try to do the history of physics, episode 7, I think. Yeah.
Okay, great. Looking forward to that.
Yeah, we are moving.
And we'll be in touch as well.
I think I'll touch upon the M theory and all. I think in that.